When I was in my school, I got a chance to learn about gravitational force, and there was a fascinating concept called escape velocity. Whenever we throw something upward towards the sky, it comes back due to the gravity. But as you try harder and harder, there will be a point when you throw something and it will never come back because it will left the gravitational field of Earth. And to achieve this, we will have to throw that thing with a velocity of 40,000 kilometers per hour. Along with this was another concept called orbital velocity. This is the velocity an object needs to throw with so that it can stay in a stable orbit around the Earth. It will neither leave the gravitational field of Earth nor it will come back to the surface. Instead, it will be revolving around the Earth in an orbit, and to achieve this, we will have to throw that object with a velocity of 28,000 km per hour. I am using two words here interchangeably, speed and velocity. Although they are two different concepts, I am doing this to make the things more understandable. As a child, the first question that came into my mind that, instead of using big rockets, can we make a huge catapult-like structure so that we can launch space shuttles into the space so that we can avoid burning fuel? It was year 2014 when I was studying in a remote village of Punjab, and a guy named Jonathan Yenny had already launched a project in Sunnyvale, California. The aim of this project was to use kinetic energy to accelerate any satellite so that it can go up to high altitudes. But instead of catapult, they developed something even more interesting. A 100-meter diameter steel vacuum chamber. In this chamber, there is a carbon fiber arm which spins with the speed of 8,000 km per hour. On one end of this arm, the payload is attached. After achieving the required speed, the payload is released through a small outlet on a trajectory path towards the low Earth orbit. But why only 8,000 km per hour? We have just learned that the orbital velocity of Earth is 28,000 km per hour. How can an object with that less speed can go up to the orbit of Earth? And that's a genuine question. When we learn how the traditional rockets work, the maximum thrust they need is at initial stages. To reach up to the velocity of 8,000 km per hour, most of the rockets typically consume 60 to 70% of their fuel just within the few seconds of launching. This is because 99% of the Earth's atmosphere lies up in first 50 kilometers of altitude, and the rockets have to face too much friction from the atmosphere during the launching phase. But when we launch payload with this SpinLaunch technology with 8,000 km per hour, within 30 to 40 seconds of the launching, the payload would be at 50 kilometers of altitude, leaving 99% of the atmosphere, saving up of about 70% of the fuel. And from that point, payloads can use their onboard small rockets for propulsion to achieve the orbital velocity, and that would be much more easier and efficient. Although this technology is still in its trial phase and they have achieved only 10 to 12 kilometers of altitude right now, but they are getting better and better with each trial. And trust me friends, this is a great step towards satellite launching technology. Although this technology is not suitable for sending human beings into the space, because while launching, the space shuttle would face tremendous amount of centrifugal force in the spinning chamber. Second important thing is, right now, the SpinLaunch can only launch payloads up to 200 kilograms. Due to this innovation, the projected cost of launching payload into the space is approximately $1,250 to $2,500 per kilogram, which is significantly less than SpaceX's price per kilogram of payload on Falcon 9, which is approximately $2,700 to $4,000 per kilogram.